Okay, so what we talked about is we have this big claim that will allow us to find communities in large social networks. And so this was the formula that we are using. That's the formula probability that two nodes U and B will create an edge. In other words, if these are friends on Facebook, that these two guys will become friends if they belong to the same community A. Let's say this is community that they play basketball together. For example, we simplified the formula. This is for single community. That's for all of the communities, taking products for all the communities that they belong to. And here in the columns are the communities, community A, B, C, and D. And we gave the likelihood for each pair of nodes, U and V, U and W, and V and W. The first one was 0.14. They have some likelihood. The second one was 0.88, had a higher likelihood. And the last one was likelihood was 0 because they do not share any communities. And so, with this big claim, what our task is. So how do we find the community membership strength matrix? So we do have that matrix that tells us the strengths that each node is likely, what is the strength that this node is affiliated with this community. And so given the network, is it possible that this is the data about all the friends and which communities they belong to? Given the network, is it possible to find this strength matrix F? And what we want to do is find the matrix that maximizes the likelihood that this matrix will generate the data, the original data. So we want to find a matrix F that maximizes the probability that F generated our graph. So that's why we have this log likelihood, and again the reason we have the log, as I mentioned earlier, is because if we don't have so we want to find the F that maximizes the likelihood that this F generates our graph. And if we don't have the log, these are just the edge probabilities. And if we don't have a log, we're gonna have a product. We're gonna have a product of these. This is the product of all the probabilities or the strengths that these two nodes will connect. And the same, we have the product of probabilities that they will not connect. So basically, we are subtracting the ones that are not going to connect. And the reason we have this log is because if we take the log, these products turn into a summation. And it's much nicer to add them up instead of multiply them, because if we multiply them, then we're gonna get more errors. The errors start adding up when we multiply. So we're taking the log, and it's called log likelihood because we take the log. Because taking the log of products, then all the products become summations. And it simplifies to sum of logarithms, and we have smaller errors. Otherwise, if we multiply them, the numerical errors are adding up. And that's why you have this log likelihood. But the idea is that we're looking for the maximum likelihood, the most likely matrix F that's going to generate our graph. So this is the summation here. Before we had the product, now we have the summation. Now we take the log and then minus. This is the probability of the edge, probability that U and V create an edge. And out of that, we are subtracting the probability that they do not create an edge. In other words, these are all of the communities that they belong to, subtracting the communities that they do not belong to. Probability of not seeing an edge. And so we have these ones here, and when we take the minus ones cancel out, and this is all that is left here. So probability of not seeing an edge. So how do we find this matrix that maximizes the log likelihood? So we can think of that as an optimization problem. And if we have optimization problem that is continuous, we can use the gradient. So we can use the notion of a gradient to solve the optimization problem. So what we have here is we're taking the gradient of that formula that we have just seen. So we're going to take the derivative of the log likelihood. So, the gradient we can think of as the gradient is the slope. So let's say if this is our function, we're gonna find the slope at a given point, and we will keep moving into the direction of the slope until we find the smallest or the lowest point of the function. In our case, we don't find the smallest point, we want to find the biggest point. So this is going to find the minimum if we go descending, and if we want to go ascending, then we're going to go up and find the highest point. So we will do ascending direction going up, so that we can find the maximum point of our function. Because we want to, so this is the derivative, because we are taking gradient. So we're going to find the maximum point in our function. In other words, we're going to keep changing our weights a little bit every time by using this gradient until they stop changing anymore. And when they stop changing anymore, it means that we have reached the highest point and our algorithm has converged. So this is the derivative of the log likelihood. This n here is all the neighbors. That is summation of all neighbors. This is the derivative of the first part of our equation. And this is summation of the non-neighbors. To a given node. So this is the algorithm. This is what we're going to do. First, compute the gradient of the row. Remember, we have a matrix. We're going to take the first row, compute the gradient. Next, we're going to update this gradient a little bit. We're going to move up our function a little bit. That's the second thing that we will do. Move it up. And we're gonna keep moving up until values do not change. When the values do not change, we have converged. Which means we have reached the maximum point and we have found the maximum of the log likelihood. We might run into a problem when we do that because some of the values might turn negative. We don't want to have negative values less than 0. If it happens that they become less than 0, we will reset them back to 0. So we are keep moving up to reach the maximum. Now, what we notice here is that this algorithm can be very slow, and the reason it is very slow is because we are taking a sum of the weights of all the nodes that are not connected to our node. So most of we're gonna subtract that non-neighbors out of the equation, and in order to find who they are, we have to scan the entire database because there's a lot of nodes in the database and we need to find out who are not our neighbors. Any of the ones that are not connected to us are not our neighbors, so we gotta look through the entire graph. And that makes this algorithm very slow. So in order to speed that up, we can cheat a little bit. We can go through the data, find out, write down what are all of the nodes of the data, and cache them. And use that information instead of having to scan the database every single time. So this is called the version 1 of this this algorithm for finding communities in large graphs. But this version 1 is very slow because its complexity is linear to the number of nodes or number of records we have in the data, and that is very slow. Now, to speed up this algorithm, we will go to version 2 of this algorithm, and that second part where so this second part that we go over all the non-neighbors. What we can do is we can cache all the nodes and basically subtract out of them the current nodes. So we're gonna subtract the current nodes and all of the nodes that are their neighbors out of all of them. So out of all the data in our database, we're gonna subtract the current nodes U and V that we're looking at and all of their neighbors that they do have connections to, and that's gonna give us these all non-neighbors. And to do that, we can cache these all the nodes and just update them every once in a while, and that's gonna save us a lot of time of going through the nodes through all the nodes every time. If we do so, before we had the version 1 had linear time, in the degree of the whole network. And now we have linear time, but in the degree of all the neighbors of a node. So the only thing we need to search is the ones that are directly connected to it. And considering the fact that most nodes have just a few connections to other nodes, that's much smaller time that it will take than searching through all of the nodes in the network. So the node connects to a small fraction of the total node network, of nodes in the total network. So what we have done is we computed the gradient, we have moved up the hill to reach the highest point in our function, so we found the maximum likelihood, and which gives us our matrix F that's gonna tell us which communities the nodes belong to in the social network. So this version 2 algorithm, when we have cached all the nodes instead of going through all of them, it's gonna show that this algorithm is much faster than some other current algorithms that exist. So this is the size of the data, number of nodes in the network, and this is the time that it takes to run the algorithm. And you can see these are some existing algorithms that search through the network for the same thing. Link clustering, click population. As the number of data increases, this algorithm starts to take a very long time to compute, and the current algorithm is taking much lower time to compute. So for example, for 5 minutes, we can process 300,000 nodes of data, which some other methods can take days to do that. If we have 100 million edges, then we can process that in about 1 day.